Welcome back to our Hypercompositional Algebra series. In the previous episodes, we introduced hypergroups, discussed their motivation, and explored their fundamental axioms. Today, we'll study one of their most important subhyperstructures, the subhypergroup. Just as subgroups play a central role in group theory, subhypergroups are essential for understanding the internal structure of hypergroups and will appear frequently throughout the series. By the end of this video, you will be able to define a subhypergroup, verify whether a subset is a subhypergroup, find all subhypergroups of a finite hypergroup, and examine examples of subhypergroups in infinite hypergroups. Let's get started. Let's begin with the formal definition. We are starting with a hypergroup with a certain hyperoperation. So we have here, this one is a hypergroup. And we are considering a non-empty subset S of H. Of course, as it will be non-empty and it's a subset of H. For it to be a subhypergroup, it should be a hypergroup under the same hyperoperation, i.e., we should have S with the same hyperoperation on H defines a hypergroup. And this one, it reminds us of the definition of the subgroup. Now the question is, how can we check whether a certain non-empty subset is a subhypergroup or not? Do we need to check all the axioms? Recall that the axioms for a hypergroup axiom. Now for associativity, the associativity is applicable for all elements in H. It means that it's also applicable for all elements in every non-empty subset of H. So the reproduction axiom will be enough. So to prove that a subhypergroup is, or a subset is a subhypergroup, all what we need is just the reproduction axiom to prove. What do we mean by the reproduction axiom? It means that we need to show AS equal SA equal S for every A in S. Now, let's try to link this one to group theory. If we have a subset of a group, in order to prove that it is a subgroup, the only thing that we need to prove are the closure and the inverse. But here it's not the case. We defined hypergroup. We did not say that there should be an inverse. We have only two axioms. The first axiom is associativity, and the second axiom, it is the reproduction axiom. We're done with the formal definition. Now let's start with some examples. In the previous episode, we explained about two hypergroups, the total hypergroup and the biset hypergroup. We'll consider these two ones and try to find their subhypergroups. So let's start first with the biset hypergroup. And for the biset hypergroup, I will take one example when H is equal to AB. So we'll start first when H is equal to AB. And we will consider the biset hypergroup, which is this one. Now, our aim is to find all subhypergroups of this hypergroup. Subhypergroup, by definition, it is a subset. So first of all, let's write all the subset of H. The singletons and H. Of course, we have one more subset, but this one We don't need it when we deal with subhypergroups because it's the empty one. So we'll check first whether this one, H1 is a subhypergroup, H2 is a subhypergroup, and H3 whether it's a subhypergroup or not. Now, if you look at H3 is equal to H, which is the hypergroup itself. So this one, it is a subhypergroup. Now, let's look at A. Remember, our aim is to check whether XH1 equal H, X1 equal to H1. But this X, remember that it is in S, which is H1 here. And H1 is equal to A. So all what we need based on this is just to find A with A. A with A, based on this, it's equal to A. So XH1 is equal to H1 X1 equal to H1. It means that this one is a subgroup. Let's look at H2. We'll do the same. So for H2, we'll do the same. X belongs to H2 and H2 is B. So XH2 is B and B with B is B, which is H2. It means that H2 is also a subhypergroup. So basically, this one has 3 subhypergroups. Now let's move to the total hypergroup. Remember, in the total hypergroup, we have X star Y is equal to H for every X, Y in H. Our aim is to define or to find all subhypergroups. So also we will deal here with subsets. H is a subset of H, and it's a subhypergroup. So this one is a subhypergroup. So we know that every hypergroup, it will have at least one subhypergroup, which is the hypergroup itself. Now, what do you think? Can we find a subset M not phi, proper subset of H that is subhypergroup of H? What do you think? Pause the video for 1 minute and think about this. Now, if M is a proper subset of H and it is a subhypergroup of H, it means that we will have A in M because it's not empty, and we have A times M star M equal M star A equal to M, right? Okay. Now, we know that A belongs to M, so at least it will have one element. A belongs to M, it means that A belongs to A star. A belongs to AM, it means that A star A is subset of A star M, right? Now, let's look at the definition. A star A, we're saying here that X star Y is equal to H for every X, Y belong to H. So A star A is H. H is subset of A star M, and we're starting that it is a subhypergroup, means that H is subset of M, and M is a proper subset of H. This one, we call it contradiction. So what can we deduce here? That the total hypergroup, it has only one subhypergroup, which is the hypergroup itself. And this one, if we go back to group theory, in group theory, if we have a non-trivial group, it will have at least two subgroups, the identity and the group itself. Now, why this fact from group theory is not here in hypergroup theory? Because in groups, the identity is mandatory to have it. Here in hypergroup, we have only two pillars. The identity is not necessarily to be there. Here we have another example. Also, it's for a finite hypergroup, and our aim is to find all subhypergroups of H. Now, this hypergroup, it's not the biset hypergroup. How do we know that it's not the biset? Because if we just look at A and A around A is H and not A. And also, it's not the total hypergroup. How did we know that it's not the total hypergroup? A times B is AB and not H. And our aim is to find all subhypergroups. Again, it's finite. We can first list all subsets, non-empty subsets of this hypergroup. We have the singletons, we have the pairs, and we have H itself. And of course, H trivially is a subhypergroup of H. Now, if we look at A, the singletons, let's check the singletons. So I will write the singletons in general, X, and X can be A or B or C. Do you think that this singleton can be a subhypergroup? Let's look at X star X. It's equal to what? X star X is equal to H. Is it a subset of X? So if we have the subset in the form of singleton, it's impossible to be a subhypergroup. What are the other options? The other option is when we have XY, X not Y, and XY can be A, B, or C. Do you think that this one could be a subhypergroup? Let's check. We're saying X is not Y, right? Now, for it to be a subhypergroup, X star X should be in it. So if I call this one as M, it should be a subset of M. But X star X is equal to H, and M is not H. What can we deduce here? That the only subhypergroup of this hypergroup is itself. And this is another example when we have only one subhypergroup of the hypergroup. Now, I will keep this one for you to think about it. You can pause the video, think about it, and let's move now to a case when we have infinite hypergroups. So far we have only considered finite hypergroups, but as we know that hypergroups may also be infinite. This example, we posted it in the previous video. Our aim is to find some subhypergroups when G is equal to Z. Trivially, Z will be a subhypergroup of Z. Our aim is to find other ones that they are not trivial. Now remember, if we have AB, A circ B, it will be equal to AX plus BY with XY belong to Z. This is the definition of this hypergroups or the hyperoperation. Let's think of 2Z. Now, why did I think about 2Z? Because 2Z is also a subgroup of Z. So let's check here. If 2Z, it will be a subhypergroup of Z under the hyperoperation. In order to show that 2Z is a subhypergroup, we need to show that A circ 2Z is equal to 2. Now, why didn't I write circ A? Because this one, it's commutative. A circ 2Z is equal to 2Z circ A. So the only thing that we need to show is A is equal to 2Z. So our aim is to show that A circ 2Z is equal to 2Z. This is what we need to show. In order to show it, we need to show that the left is subset of the right and the right. So let's start with the left subset of the right. We'll take B into C, right? And our aim is to show that A round B is subset C. Now, what's A round B? A is equal to AX plus BY. Of course, XY belong to C. But here there is something that is very important that we need to add it, that A, it belongs to 2C, right? So let's check now. A is even, belongs to 2Z, it means that it's even. And B, it belongs to 2Z, it means that it's even. Even plus even, it's subset of 2Z. So we're done with the left subset of the right. Now we'll move to the second one. Our aim is to show that the right is a subset of the left. So we'll take an arbitrary element in 2Z, and our aim is to show that this element is in A round 2Z. Now let's look at B. Can we write B as A times 0 plus 1 times C? Look at this 0. This 0 belongs to 2Z, and this one belongs to 2Z, right? So this one is where it's in A round B. And A round B is subset of A round 2Z because B is in 2Z. You can try other things as well. Now it's your turn. Pause the video and determine all subhypergroups of the hypergroup shown on the slide. Start by listing the candidate subsets that they are non-empty, then apply the definition step by step. By this, we're almost done. Just recap, we have covered the concept of subhypergroup and learned how to identify subhypergroups, both finite and infinite hypergroups, throughout concrete examples. Subhypergroups play a role similar to subgroups in classical algebra and provide the foundation for many deeper topics in hypercompositional algebra. In the next episode, we'll continue our journey by exploring other things related to our topic, hypercompositional algebra. Thank you for watching. If you enjoyed this episode and you'd like to know more about, or you have a certain thing that you would like to clarify, please leave them in the comments and I will be happy to answer. Plus, if you wish to connect or know more about me and about the series that we're doing, you can connect or follow me on LinkedIn by scanning the QR code. From now till we meet again, have a great day and see you inshallah in the next episode.